pizzas here, you can consider it a side channel. A side channel is some kind of signal coming from, well, a black box, your target, the thing you're investigating, and it tells you something about what's going on the inside. They found out that huge international disputes usually cause the big pizza spike. And, well, this has been anecdotally called the pizza attack on the Pentagon. On a more serious note, a couple of side channel attacks, examples from the recent times. You may have heard of Wij vertrouwen stemcomputers niet. I'm not going to try to pronounce that in English. Basically what they were able to do is to sniff off the air the votes that were cast on a certain electronic voting machine. And they just did this using the signals that the machine naturally produced. And, well, this is a nice TEMPEST scanner. And they showed that you can differentiate between votes on the CDA, which is a political party, or other parties. It's another example of a side channel. Even more recently, there was a couple of guys at CanSec West this year that showed that using a laser pointed at a laptop case and then looking at the reflections coming back, the vibrations from the laptop actually they related to the keys that were being typed. And if you look at a laptop long enough and the vibration of the screen long enough, you can actually deduce what somebody's been typing. So the vibrating screen of a laptop, I'm just going to check mine, actually discloses what you've been typing. So that's all very cool. Well, I've already been introduced much more ambitiously than I was going to do myself. I live in Amsterdam. I work for a lab called Riskier. We do all kinds of security testing, mostly on hardware, so like smart cards and embedded systems. Personally, I've been doing a lot of software reverse engineering. I'm a computer scientist. I'm not a hardware guy, sorry. But I've picked up quite a bit over the last few years there, so don't worry too much. And before this, I used to work for a pen testing company called ITSX. Okay, so a little overview about this talk itself. So we're going to be looking at side channel analysis. And two major components there are passive analysis, which means that we're not going to interfere with the target. We're just going to look at what signals it's giving us. And we're going to be looking at active attacks. So we're going to try to influence the device by sending in weird signals like glitches on the voltage line, sending in laser beams, all that kind of cool stuff. The targets I'm going to be talking mostly about is going to be smart cards. These attacks were mainly invented on smart cards. If the term DPA doesn't means anything to you, differential power analysis was invented about 10 years ago, and it was a huge blow to the smart card industry at that point in time, because some guys from CRI, a company in the US, they showed that they could, at that point, pretty much break any smart card. Nowadays, it's not so easy anymore, but I'll show you at least the basics on how this works. Interestingly enough, smart cards is a bit of a different world from embedded systems. So all these kind of attacks that were invented and more or less have countermeasures nowadays on smart cards are still applicable to embedded systems. The control of your target, it's a different target, but the basics apply as well. Tomorrow there will be a talk by a colleague of mine who's going to be going more in depth on how this works on embedded CPUs. When I say side channel analysis, you can break a target. I'm going to be talking about the DES algorithm later. We're going to break that now. You know that the DES has been cryptographically broken as well, but that's a different way of breaking things. Here we're going to break the implementation security. So I could use the same tricks to break AES. Well, I'm actually breaking the implementation of AES. So I'm not doing something cryptographically new here. Just to go into a few of the attack channels that you can think of. One early one that people have been looking at is timing. So let's say you have a process and it takes a certain amount of time. And depending on what's going on in the inside of the algorithm, it takes 20 milliseconds or 30 milliseconds. Now when you have this kind of knowledge, then you know, just by measuring the time, whether it's done process A or process B. And if this depends on some kind of secret being processed in your chip, then you've recovered this secret. I'll show in one of the next slides a cool example on that. Power consumption is one of the major, let's say, side channels that we're going to be looking at. You can imagine that each device uses power, but when you really start to measuring this precisely, you can see that this power actually relates to what the device is doing. So this relationship, if once you start to understand it, you can just from the power usage say something about what it's been doing. Same kind of idea with electromagnetic radiation. Every device that uses power is going to send out signals as well, and we can analyze those as well. I'll have a demo on that in a sec. Light is another attack channel. Actually, until a couple of months ago, I thought that this would only be an active channel, like you can fire lasers at something and it will change it. But then I read something about picosecond analysis of light as well. And apparently a chip is actually also sending out light. It's like a few photons every 10,000 switches of a transistor. But you can, with certain equipment, you can actually see a chip working. Now, we don't have the equipment for that, unfortunately, in our lab. But it sounds pretty cool. Now, sound. I personally never have heard a chip make any sound yet. But sound is, in principle, it's also a side channel. This has been shown also a couple years ago by some guys who were just recording the sounds of key presses. And each key actually has its own distinct fingerprint in terms of the sound it makes, it's the clicking sound. So just by measuring that for long enough, you can, by listening into somebody's keyboard, you can reconstruct what he's been typing. Now we're going to be mostly looking at power and EM here. I have one example on time. So that's what I just said. So what kind of hardware do you need for this? Well, first of all, it's nice to be able to actually measure the power. So you need some kind of oscilloscope, preferably a digital one. And you need some kind of PC to acquire this signal. Now, depending on your target, this can be just an off-the-shelf eBay scope, going up to sort of the scope that you see on the picture, which is the price of a small car, which is the kind of stuff that we use in the lab. Because when you go to the really high-end targets, you need to have some very precise measurements. But the older smart cards are really easily breakable by any, let's say, standard, easy scope. Well, you need a probe. And depending on what channel you're measuring, you either need a small resistor in the power supply to the smart card, and you can measure the voltage drop over this resistor, and this tells you how much power it's using. Or if you're going to measure electromagnetic fields, you can put a coil in the field and just measure the signals that are coming from there. And obviously you need to somehow control your target. So you need to have either a smart card reader or a contactless smart card reader. And on an embedded system, the interfaces are not so well defined as on a smart card, so you sometimes need to run your own code in the system and be able to talk to it. Now this is an example of our first generation device that we hooked up just to do power measurements. But it's basically nothing more than just a serial controlled reader and BNC connector. Let me see. This way around. And a BNC connector there just for measuring the power. So it's actually, it's not a hard build. Nowadays, actually, we put a lot more hardware into there to make it as noiseless as possible. But again, that's for the higher end targets only necessary. Now, when we're going to do EM probing, we need to have this coil. So we made it ourselves because we've actually experimented a bit with hard drive heads as well, because you can use this as an EM sensor as well. But they didn't really have the size and the particular characteristics that we were looking for. But the coil is nothing more than a bit of wire, so it's not that hard to make. What is hard to make is sort of the amplification stages that we have behind it. Because as you can imagine, the voltage differences over such a small coil are not very big. So we need to amplify the signal before we can actually measure it. Now this is what it looks like when you put some screws into it and hang it over a chip. When you have contactless cards, we built this high-end device. You can actually just put this in between your contactless card and your reader. And on the other end, you just connect it to the oscilloscope, and then you can measure what the field is doing there. Now, what we typically see is that this is nice. I mean, it's a cool experiment. But using EM, you can get much better signals than using the RF. But I mean, this is actually still more or less a direct power measurement. Because the contactless card is being powered by the field. So the more power it drains from the field, the less you're going to measure with this thing. So again, it's more or less a power measurement on a contactless card. Now, for EM, we have one more challenge than with power. With power, we're measuring the whole power over a whole smart card, let's say. But EM signals are actually very localized. And it really depends on where you're measuring what you're going to see. So this is a bit tricky to find this spot, and then we used to do it by hand, just move it and just see what your signals are. But we got a bit bored with that, so we made this cool XY stage, which basically just scans over the entire surface of the chip and just makes measurements at each point. And then you can display nicely graphically sort of the field that's coming out of this chip. This is after quite a bit of filtering. You typically are looking for certain frequency components. For instance, if this were a smart card, and on a smart card there's usually the main CPU, but there's also crypto accelerators. And these sometimes run at different clock frequencies than the main CPU. And if you go into spectral filtering, you can actually focus on those particular frequencies that you presume are the ones from the crypto clock, and that way you get a much better signal-to-noise ratio. And that sort of outputs these kind of things. And if you really want to impress your girlfriend, then you print them in 3D. Okay, so I have a quick demo here. Just a standard scanner. The only thing that's a bit non-standard about it is this antenna, which is just a coax cable with a little loop at the end. So what we're going to do is we're going to tune this to a frequency. I tried this out more or less by brute forcing before. That is tuned to the RSA frequency of, I didn't bring a smart card, I brought this embedded board, which is just a simple ARM processor. We programmed it to do an RSA operation, so it's doing some kind of crypto. We send it data, it encrypts it, and sends the encrypted stuff back. Pretty simple. Let me put it up here. And hook up the radio. Now this might be a bit noisy. I hope not. Can we hear anything? Now this is sort of the idle sound. So if maybe it's nicer if I do it like this. So I'm just going to hold the loop over different positions on the chip, and you can hear it's changing a bit, but there's not too much going on. But now I'll just start a script that'll just tell the thing to start doing RSA. So as you can see on the screen, it's sending, well, just 0 to F. This thing's encrypting it and sending the result back. And now what we hear is, it's pretty cool. I think this is a new generation of computer-generated music. Basically, it's the sweet sounds of crypto at 18.9 a.m. Thank you, thank you. But this basically shows that just the signals coming from a chip, you can deduce that something's going on in there. Now, where does this come from? The signal leakage itself actually comes mostly from the buses because they're very long lines relatively in the chip, so they take a lot of power to pull up and down. But also registers and ALUs and all kinds of transistors that are switching actually take up just a little bit of power, but enough to measure if you have big numbers of them. Now, when you start doing these kind of measurements, you will see these types of shapes. Now, when you're a bit longer into side channel analysis, you'll start laughing immediately when you see this, because this is a very broken card. This is an old one, but I'll show you what's going on. This is actually a card that's doing a pin verification. So a pin is a 4-digit number, and the card is going to decide whether this is the same pin as that it has configured or not. So in our first measurement up here, we've entered a pin that's wrong in the first digit. In the second one, we did it in the second digit, third digit, etc. Now, the pattern that we see here is this sort of bump that's happening up here. And here we see it happening once. In the second trace that we took, we see this pattern occurring twice. Now, 3, 4. Now, we're all intelligent human beings here, so I think we can already tell what this means. What you can see here is that it's actually doing an array compare. It immediately terminates after it sees that a digit is wrong. Now, that's very nice if you're in a black box, but we're opening up the black box here. So we can actually tell, just from looking at this, which digit we entered is wrong. Which means that on average, you would need 5,000. Normally, you would need 5,000 pin tries on average before you got it. Now you need only 20. So that sort of is a first illustration of the strength of this stuff. And this is just one measurement. We're just looking at the card once. Now, again, I must say, those are the weak, old, smart cards. But you can imagine that embedded systems nowadays, I mean, why the hell would you continue comparing digits if you know the answer is already wrong? From a functional point of view, it makes no sense. But from a security point of view, it does. So this is more or less what we call simple power analysis. It's actually not that simple, but in the initial paper that Paul Kocher wrote in 1998 on differential power analysis, he also introduced simple power analysis, which is definitely simpler than differential power analysis, but it's not that simple necessarily. But basically it means we're going to analyze just a few traces, like 10 or a dozen or not very many, instead of going into the statistical analysis, which I will talk about a bit later. I have an example here of the COMP128 GSM algorithm. Excuse me. And we've taken 2 traces here. Now we see the power is going up and down and something's happening here. But there's actually something interesting happening here. We see that the processes up to here are aligned. So they're doing the same things. Then here in between, something happens and they start misaligning. So you will see that this process is actually a bit quicker than this one. And after that, they go do the same thing again. Now, in this case, we had the source code of this algorithm. And we found in the C source code that a byte was being taken from a table of 512 entries. And this depended on 2 other bytes, so K and D. And K is actually the secret key that's being used. So that's the thing we're after. And D was just input data. So that's stuff we controlled, stuff that we could send out to the card. But why the hell would a table lookup, which we matched up to this part, be non-constant? It's just a memory indexing. Well, that's because this was run on an 8-bit microprocessor. So effectively, it cannot index into a 512 entry table. So what the compiler does, it looks at this C code and says, oh, that's not going to fit. So it basically splits the table into 256 entry tables. And then runtime, it will decide, do I look in table A or do I look in table B? And that's what we can see here. So there's actually a bit of time difference into depending on which table it's indexing. Now, that's all very fine, but what are we going to do to break this? Remember, we control D, and we want to know K. So we basically start off by sending D0, and then we send D1, D2, etc. So in the first case, we'll stick to these shorter traces. And at some point, at some value for D, we will see that it's actually jumping to the other table. So at that point, we know K plus D equals 256. So we've effectively broken the key there. So here you can see that even at all kinds of different levels here, you don't see any problem with the code. And when you go down deep into the assembly level, you will see that these kind of timing differences start to occur, and you can break the whole security of a thing by that. So that was more on simple power analysis, which only works if you have very leaky cards. So basically, if you look at one trace, you can see the differences. So this is typically what we would see. For instance, this is a software DES. So it's executing on a card, and it's calculating a DES. We're going to zoom into this a bit. What you see here is the initial permutation for DES guys out there. This is the first round, second round, third round. It goes on, but I left that out. We're going to zoom into this part. And we see this pattern occurring. I'm going to zoom in a bit further there. And then we actually start seeing some interesting differences. Here I've plotted 16 traces on top of each other. And you can see that they're sort of the same power level here. And here you start seeing something's happening. And here even they're going wild even further. And that's when we start cheering in the lab, when we see something like this. Because this is actually the data influence. So actually the fact that a byte has a different data value gives a different power value. That relation, that's bingo. For us, that's profit, I guess. Now that's great. We don't see that anymore because nowadays manufacturers know about these kind of things. So we typically get more traces like this. It's just one big band of noise. So you have to go into more statistical methods to actually analyze these kind of things. So the question is, where is this data being processed in all the noise that we have? So before we could just zoom in and find the different power levels and then deduce the data. Typically it's actually leaking the Hamming weight of the data. So it's actually leaking the number of bits that are set to 1. Basically because the assumption is that every bit has the same influence on the power level. That's just an aside. So the question is, where is data being processed when you're in the presence of noise? Well, in this case, we take many traces. So we take a lot of these measurements. And for each measurement, we also register the data that we send to the card. And typically what we would do if we're analyzing, for instance, an AES implementation or a DES implementation, we send out random input data. So it's uniformly random. And of course, we know the data that we send to the card. We know the data that's coming out, but we don't know the secret key. So that's what we're after. What we're going to do is we're going to focus on one bit of one variable in the process. Now, this sounds a bit complicated, but for now, let's just presume we're looking at the first bit of the data block that we're sending as input. So it's either 0 or it's 1. So by looking at this bit, we can group all our measurements into two big bins. One where this first bit of input is set to 0, and one where it's been set to 1. Next thing we do is we take these big bins of traces and we average them. So we end up with 2 traces. And the interesting thing is that the only difference between these 2 traces, the only statistically significant difference between these traces, is the fact that these bits are different. Because all the other bits that we send, they're uniformly random, so they're not correlated with this one bit that we're looking on. So the only statistical difference that we've made here is that one bit being processed. So if we subtract these traces, we're actually going to see noise except in the places where this bit has caused some kind of influence on the data. And this is very strong, because we don't always take 1,000 traces, sometimes we take 1,000,000 traces. So we can detect differences in voltage in the tens of millivolts. It's amazing. And it's very hard to protect against as well. So that's what's called a differential trace. So it's a trace that shows sort of over time, it gives peaks on where statistically this one bit that we're looking at has caused an influence on the power. So the input for differential trace is just n traces with some known variable. It can be input, output, anything else, but you have to know it. And the output is a trace like this. Now this actually is the thing that I ran on the DES again. And what you see here is, so it's the first bit of input to the DES algorithm. So that will correlate here during the initial permutation where the bit hasn't been changed yet, but it's just being shifted around. And then later on it will correlate in the S boxes, and the correlation actually goes down, because that's what a crypto algorithm does. It decorrelates the input from the output. Now, that's all great, but what if we don't know the value of the variable for each trace? Well, basically, we're screwed. You need to know the data. But it's not as strict as that. It also works if we know that the data might be restricted to some set of, some collection of data. So, for instance, let's say we've taken, well, in this case 4, but n traces, and we know that the data is either 0, 1, 1, 0 for these traces, or it's 1, 1, 0, 1. It's in one of the hypotheses. Then we can actually just calculate the differential trace for each of these, and I'll show you what the effect is. Because basically, we presume that one of the hypotheses is right. Now, we don't know which one beforehand, so we're going to try them all. So either a hypothesis is right or it's wrong. So let's first see what happens if you take a wrong hypothesis. Again, we're going to calculate this differential trace. So the first step is we're going to group the data differently. So here we've grouped them by the wrong data in both cases. Now if we calculate the average here, these will statistically actually not differ at all, because you've done something wrong and it just all gets messed up in the grouping. So what you see is noise. Now if we group according to the right hypothesis, we get back into the original situation where there is a statistical significant difference, and when we subtract, we actually get these peaks. Okay, so that's all kind of tricky and to get your head around, and it's going to get even more complicated in the next few slides. But the bottom line is, if our hypothesis is incorrect, we get nothing, and if it's correct, we see these peaks. Up to now I've been talking about this input bit, but the cool thing is there's no restriction on that. I can also start predicting stuff that's going to happen inside the algorithm. So this tool actually allows you to, if you have a restricted set of hypotheses on what the data is being processed inside the algorithm, you can also run this trick. Now that's kind of cool. So now we're going to look in what the effect of this is on crypto. So here I plotted the DES algorithm, which is still the most widely used algorithm in smart cards nowadays. Actually triple DES, but it's made up out of 3 DESs, so we're just going to break 1 DES. So as you may know, you send in plain text, it does some kind of permutation, and it goes through this Feistel scheme, and then the answer comes out. Now that's great. And in every round, it mixes a round subkey. Now we're interested in these guys, because if you, in the case of DES, if you have 2 round subkeys, they will actually make up the full key that you're looking for. Now if I zoom into this Feistel function, what you see is that the data is going in, it's being split in 2 halves, and half of the data ends up in this E permutation and gets XORed with the subkey. So we actually know the data going into this algorithm all the way up to here, Then it gets XORed with subkey, and then we're lost. It's 48 bits. We don't know what they are. But the next step is that they're being spread out over all these S boxes. So the S box output here, so 1 bit of S box output depends on 6 bits here, which actually depends on 6 bits we know, and 6 bits of subkey. Now that's the kind of thing that we're looking for when we're doing, in this case, differential power analysis. We're going to chop up the key into little bits, in this case just 6 bits, and we're going to try to break them one by one. So let's again assume we have 1,000, 1,000,000, a bunch of traces. For each of these traces, we know the data that we sent in there. So for each trace, we can calculate the data all the way up to this E permutation, up to this XOR with the subkey. After that, again, we're lost. I said that. I said this as well. We know this part. We don't know the subkey. So that's our question. How are we going to figure out these 6 bits? Well, we're going to run what's called differential power analysis on it. We're just going to try, I mean it's 6 bits, 64 possibilities. We're just going to presume each subkey in turn. And then we're going to calculate these differential traces based on each subkey. So in the first case, we know the data going up here. We presume the subkey is 0. And we input this into the S box, and we're going to try to predict this output bit. So this is again the hypothesis testing I've been talking about before. So we take n traces, and each of these 6-bit subkeys leads to a different hypothesis for the S box output. So we're going to end up with 64 hypotheses, of which one must be right. One of the subkeys must be the right subkey. And we're just going to calculate a differential trace for each of these 64 possibilities. Now, what you get is this nicely twisted number of traces. I'll flip them around for you, but this is just to display to you that we have n traces, but we always end up with 64 differential traces. What we see is that there's actually one key candidate where we see these peaks. Now, what does this mean? If we see peaks, that means that we've done the grouping correct in the differential trace. And if we've done the grouping correct in the differential trace, that means that the real data actually must match our hypothesis, which means that we know the subkey for this. Now, if we just keep on doing this for all the S boxes in the first round, and then we do it all for all the S boxes in the second round, we can actually deduce the full key. So using this method, we can go from knowing nothing, just measuring the power, doing these differential traces, and retrieving the key from an implementation. And this works just as well for AES or for more like asymmetric crypto algorithms like RSA. There's different techniques. But this is really cool, and it's mind-blowing the first time I saw it. So, well, once you've done that, I guess you can go home and have a beer and enjoy your victory. Just a small reality check. Of course, smart card manufacturers know about DPA, so they implement all kinds of countermeasures. And for us, it's often difficult finding the correct kind of filtering and alignment things. But it's still, in the end, it boils down to doing the same type of analysis. Your pre-processing may be a little bit more complicated. Countermeasures, we find them in both hardware and in software. So in hardware, we see like noise generators on the power line. We see random pipeline stalls to create misalignment in the processes. There's all kind of things going around. On embedded systems, we don't see them that much. So that's more of an easy target in a way. To go into fault injection, that was sort of the side channel analysis part. This is the side channel attacks, or the fault injection. We're going to try to cause a temporary fault in the program. So we're not going to burn our chip, hopefully. We just want to switch one transistor at some point in time and see what it does. This has actually been traditionally studied in the failure analysis. For instance, in space technology, they have a problem there with X-rays and all kinds of radiation bombarding chips and causing all kinds of failures. So that's where it comes from. And there's different channels that you can glitch. You can glitch the supply voltage of a chip. You can glitch the external clock, which is on smart cards, the clock is provided externally. And you can go into the cool kind of laser glitching stuff. Now, the effects of fault injection can vary. But basically, your targets are branches, like if pin is correct, then do this, else fail. Well, that's a nice one to glitch. All kinds of state variables, for instance, cards that are able to lock themselves, you could unlock them. Crypto is a whole different ballgame. You can actually insert errors in your crypto algorithm, and by comparing them to regular executions, you can derive the key, which is differential fault analysis. Skipping instructions you could do. Sometimes you can null crypto bytes, thereby reducing the entropy of the key. I mentioned differential fault analysis. Bell core attacks are pretty cool. There's actually one attack that if you have an RSA Chinese remainder theorem implementation, you can actually glitch it once and once do a normal execution, and just from the difference of those two you can recover the entire key, which is pretty strong, you could say. Now if you really want to kill your target, that's not too visible. There's actually somebody who tried to do fault injection using a microwave oven. That was more of a temporary, or more of a permanent glitch. Now this is the kind of thing that we use in the lab for glitching right now, both voltage and clock. It's an FPGA-based machine, which basically allows you very precise control over your glitching. So what we see here is if you, for instance, do a very quick clock glitch, you can skip instructions that way. If you do voltage glitches, you can see that if there's, for instance, a fetch from memory, that typically takes more power. If you put the supply voltage down right at that moment, you can actually read either 0 values or 1 values. So there's all kinds of cool things there. But we also use this same thing for triggering our laser setup, which is very cool. So optical fault injection was actually originally used to simulate X-rays in space. So X-rays are quite high energy radiation that triggers all kinds of faults in your chips. And some guys figured out that actually visible or near infrared wavelengths actually are much more effective in glitching chips. So what we do is we implement two types of attacks. One is a front-side attack, where you're looking actually at the chip and you're shooting with red lasers. Because the idea is that depending on the wavelength, you get more or less penetration through your chip. And when you're on the sort of the business side of the chip on the front end, you can shoot it with a red laser, and you can have very effective glitching. Whereas if you're on the back side, you're actually looking at the substrate, which you have to penetrate all the way to the gates, and there you need to cause a fault. So that's why we use infrared lasers for that. We need to access the silicon to actually get to this. So I've actually heard of some guys who are able to flash right through a card, like they don't even need to open it up. But with a flashlight, you can just sort of glitch all the way inside there. We try to have a bit more control, so we actually need to open it up. This is what the front side of a smart card looks like when you drill away the contact pads. And you're actually looking at the back side of the chip there. So you're looking at the substrate. So once we see this, we're going to use the infrared laser. We can also do chemical etching on the back side. And then we're actually going to see the front side of the chip, which shows us all the gates and everything. For that, we use fuming nitric acid, which is a fun thing to play around with. It eats away all the epoxies, but it leaves the chip intact. Well, I guess you only try this when you're wearing safety goggles. So that's actually one of the smart card dies that you can look at. This is a bit of a dirty one. You see a lot of epoxy spots still on there. We found out that when you really want to have it clean, you're actually going to kill your card typically. So we usually don't go all the way, we just leave it a bit open. What you also can see is some of the more secure chips that actually have an entire layer, an entire active shield covering the die. And so you will just see like a snaking pattern going all the way over the chip, which is trying to prevent you from doing this kind of stuff. Now there's a number of low-techs low-tech attacks out there. One is using the photo flashlight, what I mentioned. You can actually also use this when the chip is opened up and use an aluminum foil with a hole in it. And you can use this to flip individual memory cells. You can use one of these guys, laser pointer as well. Same idea, you have better control over where your light is going. One of the things these are, well, this one is 5 milliwatts, I think, yeah. The one we use in the lab is 150 milliwatts, so you sometimes need a bit more power. The challenges here are you need to have some accurate triggering, accurate focusing, and the power level is sometimes something you need to adjust. So this is what we have in the lab currently. Like I said, we have a 150 milliwatt red laser. We have a 10 watt infrared laser, so that's one where you really don't want to stand too close when it's operating. We have this XY gauge for scanning the surface of the chip, and we coupled it to the device I showed you before just for this accurate triggering. This device is actually not on the picture right now. This is when we're still playing around with it. So you see a piece of paper here, and we're actually writing our names on like a micron scale by burning holes in it. I still need to make a module to imprint a bitmap or something on that scale. That would be kind of cool. So once it starts operating, it actually looks like this. So you see the chip die, and it's scanning over it, and each time it's sending in commands, it's shooting the laser, looking at the output, and trying to analyze what's going on there. So that's pretty cool. This is actually the same chip that you saw before. This is a little bit unrealistic. I made this because you can see it for visualization purposes. But normally the laser is on so short that the camera wouldn't be able to capture it. But sometimes longer glitches also work. So the challenges when you're doing this kind of voltage injection is mostly finding that sweet spot in time or location just to glitch the right transistor. Nowadays smart cards have a lot of sensors in them as well. So they actually will sense light, or they will sense all kinds of glitches and then kill themselves. Well, obviously you need to avoid those kind of spots. Now we are quite clever with actually detecting that we're being detected, because the card will show different behavior, so we just cut the power at that moment. But you need to be kind of fast in there, as you might guess. But before that, there's a few stacks of dead cards in our office. And you need to have accurate triggering. So you need, nowadays, they all cause kind of timing jitter, so you need to really look at the signals there. Now, countermeasures to all these kind of things, I won't go into it in depth, but all the DPA attacks were first published by Paul Kocher from CRI, and they have patents for all these kind of things. So if you need to implement one of these things, you have to ask their permission. Conclusions. Side channel analysis, voltage injections, they're actually quite diverse fields. You need to know something about computer science, electrical engineering, crypto, even statistics. But for me, that's the fun part. I like a challenge, and I like multidisciplinary fields. Implementing countermeasures correctly and consistently is very hard. We see that. All these things are known, but people make mistakes, and also designers do, and it's our job to find out that they did. And that side channel threats pose, side channel attacks present a serious threat to a wide range of devices. And it's becoming more, I wouldn't say common yet to do it on embedded systems, but it's getting there. Lots of times the logical attacks are not working anymore, so people start to fiddle around and try to do these kind of things. And there's only one really way to really figure out if your device is secure, and that's just to measure it. So some more cool talks that sort of relate to this topic. I think after this, even in this room, Andreas will be talking about TEMPEST for the casual election hacker. So that's looking at the emanations. Tomorrow, Job de Haas, a colleague of mine, will talk about side channel and embedded. So that will be exciting. And Sunday, Travis will talk about more or less direct probing of things. And here's, I'll post the slides on the wiki later so you can read these references. Okay, so that's it. Thank you very much.
All right, we just have a few minutes for questions, and I believe the microphone is there for anyone who does have a question. Step up.
I've heard of another technique for reading out the status of like bits on transistors, which is to use lithium niobate as a substrate to coat the surface of the chip, actually, and then shine a laser at the lithium niobate because the properties electrically will change the optical properties if there's a bit set underneath. Have you tried that?
No, we haven't tried that, but it sounds pretty cool. One of the things that we haven't tried but that I know of is that you can actually do a simultaneous voltage injection using laser and also doing the power measurement. And depending on the state of the memory cell, the power actually changes or it doesn't change. So you can from that read again the bits in the memory. Yeah, go ahead.
So it strikes me that a potential countermeasure to differential power analysis would be differential circuitry. So you do your gates with matched sets of transistors. You've got one doing one operation while the other, a micron away, does the opposite. Is that one of the countermeasures that's being used?
We have seen it, but obviously this requires doubling your entire circuitry, which is a bit expensive. But it's a technique that exists. Yeah.
Okay.
Yeah. This actually works on power because you flatten the power, but basically against EM it doesn't really do that because you have this localization property. Any more questions? Okay. What?
Okay, just some last announcements before you run out. Thank you very much.
Yeah. Thanks. Thanks.
Most of this you already know, but anyway, the iPhone talk that was scheduled for this very Monty Hall at 7 o'clock has been canceled. A reminder that at 11 o'clock, there's a WikiLeaks panel discussion here. You may not have heard yet, which is starting now. 2 talks have been moved. Relaunch Bits of Freedom is in the 2 envelopes tent, and Tempest for the Casual Election Hacker is here. So you're in the right place if you're here for that. On the other hand, you're in the wrong place if you're here for the other thing. Also, when you registered for this conference, it said that you were probably a volunteer because, well, we're all volunteers in this life. So we need more volunteers. And if you could go to field J to the volunteer desk and say, use me, because that's part of who you are. You want to be used. So go get used. Thank you.